Today, I'm going to present to you our work on TermiNeRF, or Ray Termination Prediction for Efficient Neural Rendering. We focused mainly on speeding up the rendering process of neural radiance fields with efficient prediction of ideal sampling locations along the ray. To put this problem into perspective, we have to look at how neural radiance fields, abbreviated as NeRF, works. It uses MLP to approximate a 5D function which maps XYZ coordinates of a 3D point and the corresponding viewing direction to the color of the point and its optical density. The color is fairly straightforward. The optical density is related to the probability that a light ray would terminate at this point. For each ray, hundreds of points are sampled and separately evaluated with multiple networks to obtain their optical properties. However, as we can see on the illustration, only a small fraction of all the samples contribute towards the final color of the ray. Some points are already occluded, while other points are completely see-through with density close to zero. This leads to a substantial amount of network forward passes that do not yield any results and could be skipped. The authors of the original paper mitigated this issue with so-called hierarchical sampling. The points are first sampled from a ray with a uniform distribution, and each point is evaluated with a coarse network. The coarse network determines where the volume of the rendered object is located along the ray. This, in turn, gives us the sampling distribution in the form of weights along the ray that can be used to sample further 128 points. When all the points are evaluated with the second, fine network, the results can be aggregated into the RGB color via volumetric rendering. Notice how this approach still requires hundreds of sampled points and the network forward passes. Our work on TermiNeRF builds on top of this architecture, where we simply swap out the coarse network with so-called sampling network. The sampling network takes the whole ray as the input and produces the sampling weights. The sampling network approximates the distribution of probable ray termination locations. It does so in only one evaluation, while the size and the architecture of the network stays the same as the original coarse network. And the difference in the number of parameters is only due to the different sizes in the input and output layers. When integrated into the pipeline, the distribution can be used to determine the sampling locations for the color network, which renders the color in the same way NeRF does. The sampling network can not only do one-shot weights prediction, it can do so more precisely than a hierarchical sampling approach. This way, it was possible to lower the number of the color, previously fine, network samples from 128 to just 16 without noticeable loss of image quality. Now let's take a look at the training of the sampling network. As our approach does not utilize any prior depth or geometric data, we first train the standard NeRF with only RGB images. Instead of RGB values, we can obtain the ground truth sampling weights from the fine network. The same way, the pipeline extracts them from the coarse network. We use these weights as a training signal for our sampling network. The color network is initialized with the NeRF's fine network parameters. Once the sampling network learns to predict the volume locations of the rendered object, we can further fine-tune the color network. Even though the sampling network and NeRF's coarse network produce similar results, they are not the same, and further fine-tuning of the color network is necessary to accustom it to the input from the sampling network. This way, we make sure the color network is not wasting its capacity on locations that were previously falsely predicted by the coarse network. However, we can take the training one step further. The same way the weights were collected from the coarse and fine networks, we can collect them from the color network too and use them to further train the sampling network. More precise sampling network means better samples for the color network, which in turn means better depth data. The joint training of both networks in alternating steps creates a positive feedback loop that helps both networks to produce more accurate results and images. Talking about results, we can take a look at some. We split the results table into separate brackets based on the relative rendering speed in comparison to the original NeRF approach. In all the rendering brackets, we compare our method not only with the original NeRF, but also with NeRF with the number of samples reduced such that the number of network forward passes matches our method. We can see that even in the second rendering speed bracket, that is roughly 8 times faster, our method produces the results that are still comparable with the original method in terms of both peak signal to noise ratio as well as perceptual loss. And the third bracket, we can see that 16 samples is probably as low as we can go in terms of samples for our method, while still producing meaningful results. With a lower number of samples, the image quality drops rapidly. More in-depth comparisons with the NeRF as well as other related methods can be found in our paper. In the next couple of videos, we offer you the qualitative comparison of our method. As this scene contains multiple layers of volume, the windmill enclosed in the glass case, a high number of samples is necessary to produce a good-looking image. Without any prior depth information for each new scene, new NeRF networks have to be trained. And this process is just as inefficient as rendering. However, once the sampling network is trained on one scene, it can be reused on scenes with the same or similar geometry with just different colors, textures, or lighting conditions. With pre-trained sampling network, the color network can be quickly modified and fine-tuned to produce the new scene. In the video, you can see the renders from our pipeline and the corresponding amount of time it took to train the color network to adapt to the new scene. The training was performed on a single GTX 1080. We can see the color network can be adapted in minutes instead of hours or days with the original NeRF. Here we can also see the depth maps produced by the sampling network. The produced depth map often isn't 100% precise, but it does not have to be. False negatives are easily handled by the color network, as those samples will be evaluated as points with no opacity. However, false negatives are hard to recover from. Once the color network does not receive the sample on the input, it will never learn the true volume and color of the object and will produce image with visible artifacts. This is especially visible on the bottom right video, which features the sampling network trained on a standard depth maps with a single depth value per pixel. A single depth value per pixel cannot capture the multi-layer volume nature of the object. The sampling network trained on RGBD data leaves the color network powerless to learn and subsequently render the correct image. In this video, we presented you with the TermiNeRF, an approach that does one-shot ideal sampling locations estimations, which can be used for more efficient neural radiance fields rendering and training without the loss of image quality. Thanks for watching.